So today we're going to begin our discussion on intermolecular forces. At this level, we're going to use our knowledge of intermolecular forces to make predictions about viscosity and melting points and boiling points, vapor pressure. When you continue in either your biology or maybe biochemistry, you're going to see how intermolecular forces play a critical role in protein structure, protein folding. I'm sure some of you or most of you have heard about how DNA has that helical spiral shaped structure, right? And that's due to intermolecular forces. That's how the DNA is able to maintain that really interesting shape. So we're going to start with ion-ion. Your paper has an arrow that is at the bottom near London dispersion and goes all the way up to ion-ion. So why I put that arrow there? Ion-ion is the strongest of all the intermolecular forces, and London dispersion is the weakest of all of your intermolecular forces. So basically this arrow on the side of the paper there represents increasing strength of the intermolecular force, and that's measured through energy. How much energy would it take to disrupt that intermolecular force? Ion-ion is a weird one because up until this point, you've always thought of it as a bond. So an ion-ion intermolecular force is just an ionic bond. And the types of molecules involved, well, maybe molecule isn't the best word there. Basically, what we need to have is a cation and an anion to see ion-ion forces. So cation and an anion, two oppositely charged ions. Sodium chloride is a great example of ion-ion intermolecular forces. So you have sodium ion, so it's got a +1 because it's literally lost an electron, right? And then you have chloride, which has the -1 because it gained an electron. So in between these two, we're going to have a very, very strong force. The sodium chloride actually forms a crystal lattice structure. So if I draw like a cube here, so in terms of our definition, for an ion-ion intermolecular force, we basically have a cation, which is then attracted to an anion, which is then attracted to another cation, and so on and so forth. This force is so strong, maybe put this under other notes, that ionic compounds exhibit the highest melting points and boiling points. So this is an extremely strong force. However, you can think about it two different ways. So for chemists, we think of it as an extremely strong force because in solid form, it would take so much energy to melt, for instance, table salt. Try to melt table salt. It's just not going to happen. However, from a biological perspective, you might think, well, that's a really weak force. And the reason being is because we know that a lot of our ionic compounds tend to dissociate in aqueous environments, and a lot of biology happens in aqueous environments. So it depends on who you ask. If people are thinking of it as a very weak force, and that would be specific to an aqueous environment where it's easy to disrupt, or a very strong force, when it's in solid form, forget about it. The melting points are over the top. All right, so for ion-dipole, what we're looking at is some kind of ion, positive or negative, and polar covalent compound. So water is considered a polar covalent compound. And let me draw an example of this one over here. Why water is polar covalent is because we have oxygen, which is very electronegative, right? And so the oxygen is basically pulling the electrons towards itself. Which creates what's known as a negative dipole. So I'm going to represent that as lowercase delta with a negative sign. Let me maybe draw this over here. So this is a negative dipole. It's a partial negative, or if we could also do a positive dipole. We could call it a partial positive, just change that to a positive sign. So these guys, the hydrogens, since the electron cloud is being pulled towards the oxygen due to oxygen's electronegativity, extreme electronegativity, hydrogen's kind of devoid of electrons, right? So it has positive character to it. However, it isn't as extreme of an example as sodium. Sodium completely lost that electron, and that's why it got a +1. In a polar covalent molecule, we see hydrogen kind of losing the electron, but it's still sharing it at the end of the day. So that's why we're going to do a partial positive. It's not a full-on charge. So once you have this polar covalent compound, then the ionic compound, for instance, again, let's do sodium chloride, can come in and nestle itself, and we're in an aqueous environment now, so it's going to disassociate, and it's going to find nice spots in between the positive and negative dipoles. So for instance, here's a negative, so I would expect like a sodium, since it's positive, a sodium ion to kind of be in the vicinity of that negatively charged oxygen, but it's not a full charge, just a negative oxygen. And then next to the hydrogen, I would expect like the chloride to be somewhere over there, and so on and so forth. Like they just kind of find the most electronically stable and energetically stable positions to offset the charges. Positive and negative, opposites attract. So for our definition, I updated the border here to have purple bonds, just to emphasize that bonding within a covalent molecule is considered an intermolecular force. And then we have our cation, so something like the sodium ion, attracted to the negative dipole of that oxygen. And then we have our chloride, our anion, attracted to the positive dipole, which for a water molecule occurs on the hydrogens. The orange lines represent that intermolecular force, so the force of attraction between different things. So as we move down our table and start discussing intermolecular forces that are slightly weaker, I want to emphasize how you can figure out the pattern. So on the top, we had ion-ion. So two things that exhibit full-on legit charges. After that, we have ion-dipole. So we have something that has one of those real charges, a full charge, and then something that's just polar and has a partial negative or a partial positive. Now we're moving on to covalent compounds, and their intermolecular forces are weaker because they don't dissociate and form ions. Hydrogen bonding will be the first one. And with hydrogen bonding, so I always think about, this is kind of silly, but ET. So ET phone home, like when we're little, And so I need the phone, and I need a hydrogen directly attached to something on the phone to have hydrogen bonding. So types of molecules, we need hydrogen, obviously, thus the name, directly bonded to the phone. And again, these are going to be covalent molecules that we see exhibiting hydrogen bonding. So this is a misnomer in that it's not named correctly. It's not bonding at all. We're talking here about an intermolecular force, but they call it hydrogen bonding. So keep it in the back of your head that it's not a bond, it's an intermolecular force. The combinations that can happen have led to confusion in the past. So water exhibits hydrogen bonding. I think that's the most straightforward example. So we have hydrogen, and water is covalent, and so I'll do the intramolecular forces in purple here. It's polar covalent, and we know that the oxygen is going to have a negative dipole associated with it. And so what's going to happen is that the negative dipole on one molecule is going to be attracted to the positive dipole on another molecule. So I'll do my negative, positive dipoles. And then in orange here, I'm going to do my intermolecular forces. This illustration here with the two water molecules is an example of a pure compound that has the capacity to exhibit hydrogen bonding with itself, right? Between different molecules, but in a pure solution. We can also have hydrogen bonding occurring in mixtures. So one example of that would be ammonia. Ammonia would exhibit hydrogen bonding by itself because it has the H directly bonded to the phone. So if something can exhibit hydrogen bonding by itself, then it can also exhibit hydrogen bonding in a mixture. The nitrogen is very electronegative, so I'm going to give that the negative dipole. And then the hydrogens will have positive dipoles. And then we'll see hydrogen bonding between the positive dipole of the hydrogen, say on the water, with the nitrogen here. It could also go the other way. We could do the hydrogen on the ammonia with an oxygen on the water. The possibilities are vast. The last situation that we need to consider is when we have molecules that have F, O, or N, but they're not going to exhibit hydrogen bonding by themselves because they don't have H directly attached to the phone. An example of this would be formaldehyde. Formaldehyde has, it's the same formaldehyde they use with dead bodies, right? Formaldehyde has a carbon in the middle. So that means that by itself, in a pure solution of formaldehyde, we're not going to see hydrogen bonding. These hydrogens are not electropositive enough because they're not. What did I tell you? All right, it should still be recorded. That means in a pure solution of formaldehyde, we're not going to see hydrogen bonding with other molecules of formaldehyde. These hydrogens are not electropositive enough because they're not directly attached to the phone. However, this oxygen's still electronegative enough that it will exhibit hydrogen bonding with something like water or ammonia, something that does have the H directly attached to the phone. So this oxygen with this hydrogen would also be classified as an example of hydrogen bonding. So in terms of our definition of hydrogen bonding, we're going to have the positive dipole of a hydrogen, and that hydrogen has to be directly attached to the phone. And that's going to be attracted to another F, O, or N on a different molecule. So for dipole-dipole intermolecular forces, we need polar covalent molecules. How do we identify a molecule as being polar covalent? Well, for me, it's always been a matter of looking at asymmetry, because when you have a polar covalent molecule, you're going to have an asymmetrical distribution of the electron cloud. And that's typically due to the presence of a pretty electronegative atom within the molecule. We're going to practice this though as we get into our examples. An illustration of this. So we've already used water to death. Water is polar covalent. In fact, hydrogen bonding is just an extreme example of dipole-dipole. But let's use something that wouldn't qualify for hydrogen bonding. So hydrobromic acid. So we know that the shared electrons, like we just talked about electron distribution and the orbitals. So we know that there's a higher probability of finding those shared electrons somewhere in the vicinity of the bromine. We don't know where they are, right? But they're probably near the bromine. So that gives the bromine a partial negative charge. Hydrogen then becomes, has a positive charge associated with it, but not a full charge, right? Just partially. The opposite dipoles then are going to be attracted to one another. So bromine is going to be attracted to hydrogen, and so on and so forth. So in terms of our definition, we have the positive dipole on one polar covalent molecule is attracted to the negative dipole on another polar covalent molecule. So the weakest of all of our intermolecular forces are known as London dispersion forces. This type of intermolecular force occurs in all molecules and all atoms. It doesn't matter if it's polar or non-polar, it just has to have electrons, and it's going to exhibit London dispersion forces. So what I've drawn here is two molecules of ethane. They're non-polar, so they wouldn't qualify for dipole-dipole or anything else. I have identified them as non-polar for two different reasons. One is that they're very symmetrical, and the second reason is that the electronegativity values between carbon and hydrogen are very similar. So if you have a molecule that just consists of carbon and hydrogen, it's automatically going to be classified as non-polar because the electronegativity values are so close. However, it still has a bunch of electrons. So what happens is that we have this induced dipole or this temporary dipole. So something else comes along and pushes or pulls those electrons, and all of a sudden the electron cloud temporarily moves to this side of the molecule. So here I'm going to use our same notation, but I really, really want to emphasize that this is a temporary dipole. And then this side would be a little bit positive for a brief second in time, and then this one does something similar. It's almost like a domino effect, because once you induce a dipole in one molecule, it's going to induce a temporary dipole in the second molecule. So then on this side, we have the positive temporary dipole, and that one has the electron density, just for a second, millisecond even. So the negative temporary dipole and the positive temporary dipole then experience a very, very weak intermolecular force. And we could justify how weak it is, right? Because it's temporary, so therefore it's easy to break, easy to disrupt. So in terms of our definition of London dispersion forces, we have a temporary or induced negative dipole that's temporarily or just for a brief second attracted to a positive dipole that's also induced or temporary. So again, with everything being temporary, the attraction is very quick and it's a very, very weak intermolecular force exhibited by all molecules that have electrons, which is all molecules. So we haven't taken too many notes about the other intermolecular forces. However, London dispersion, even though it's the weakest intermolecular force, actually has a lot going on in terms of how strong it is. So one scenario that we want to consider is when we have two molecules with the same formula. These are called isomers. My example here is pentane C5H12. So we can connect them different ways. That's the definition of an isomer. So same formula connected different ways. If we connect them in a more linear fashion, I know carbon has a tetrahedral shaped molecule or central. Carbon is I know carbon is a tetrahedral shaped. How would I put it? I know this carbon will be tetrahedral in and of itself. All of these carbons are tetrahedral. However, overall, the molecule is very linear, right? We've connected them all in a row. Again, a bunch of tetrahedral carbons, but this time in this particular molecule, they've been connected to kind of form a ball or a sphere. So we have this central carbon and then all the carbons coming off of that. So when you have a mixture of these more linear shaped pentane molecules, they are going to exhibit a stronger London dispersion. And that's because their electron cloud is visible. So most of the electron cloud, if not the entirety of the electron cloud, can be felt by other molecules surrounding it. When you get something that's more spherical in nature, a bunch of the electrons, and so a bunch of the electron cloud is going to be in the middle, and it's not going to be able to interact with anything around it. So only the outside layer of electrons will be involved in creating the London dispersion force when the temporary dipole occurs. So to summarize, if we have more surface area, which is associated with these longer linear molecules, then we have more exposed electrons, and then therefore we have a greater London dispersion force. The second scenario we want to consider is when we have two of the same shape. Over here we have differences in shapes, but the same size. Over here we have two things with the same shape, but they have different masses, and they have very different numbers of electrons. So the first one is methane, and then the second one is carbon tetraiodide. Carbon tetraiodide has a lot more electrons. So, and the easiest way to think about that, we don't have to count all the electrons. We could just generalize. If a molecule has a higher mass, then we know it's going to have more electrons and therefore it's going to have or exhibit greater London dispersion intermolecular forces.